Hi there. So in the data that you receive and the cases, you might realize that you have a compressible data here. So in this video, what we're going to address how to set up this compressible case. So see that you have compressible, incompressible, you have velocity profiles also. So to set up this one, it's not very different. It's pretty much since are the same, but the only thing that you need to know how to compute fluid properties. So that's what I'm going to show you how to do here. It's not that difficult. And in the cases that you have, okay, so you have this case. Okay, so if you go in Fluent mesh case, you go into Turbulence, see here that you're going to have this one YP1 heated wall. This is the compressible case. So let's open this one. So we don't need to do mesh anything, okay? We have everything predefined here. So I'm just going to address a little bit how to set up things, okay? So I already opened Fluent here, and if I go here, read case data, okay, I'm reading that case. So there in this case, just to remind you that you have the cast where you have mesh and setup, and the .dat where you have the solution, okay? So we're reading the solution, okay? See here that plot, you have the convergence rate and everything. And the difference here that now you have energy equation in this case. So how do we set up this case? So let's go back here in the vertical workflow, okay? And we go to the first step, nothing changed, okay? Everything is standard. Now you go models, and when you go in models, besides this model, the turbulence model, we have another model, which is the energy equations. So you need to enable this model. So by default, this one is disabled. When it's disabled means that it is incompressible, okay, density constant. When you enable, now you enable the equation of a state to resolve the energy, okay? So see that in this case, I cannot disable because I have that energy equation. No, the way to compute density enabled somewhere else. But this is how you proceed. Enable this, and now you go into materials, and see here materials. Here's where you set up how to compute density and all properties. Okay, there are models to compute this. So this is the most classic model, the ideal gas, but you have different ways to compute it, okay? So for instance, if I go here and put constant, this is in compressive flow. So now when I put it constant, if I go back here, I can disable this model. It's not, okay, viscosity method also, I need to put it constant. And as you go here, you can disable, okay? So this is how we were running previously. Now to enable the energy equation, enable this model, okay? And now when you go to flow material fluid property, you can choose the model. So density, choose your model. So let's say that the most standard one is the ideal gas. So you have the equation as a state, and from this equation it will compute density value according to temperature or pressure. And the rest of the properties also you can define models. So we can do it also for viscosity, okay? So in viscosity, okay, let's use the Sutherland model, okay, and 3 coefficients, okay. And as you want, you can do it also for thermal conductivity. You have different models. You can have polynomial models. It's up to you, okay? But these are the 2 models that we're going to use, okay? And we enable the compressive flow. That's all. The rest is pretty much the same, okay? So now when we are working in compressive flow, this is important. When you go in cell zone conditions, remember that previously I mentioned that this is a constant, the pressure. Now in compressive flows, this is important. Why? Because if you put this to 0, means that you are working in vacuum. And in the vacuum, remember also in the theory, we studied the Knudsen coefficient and those parameters. The Navier-Stokes equations are not valid anymore. So you have to be careful, okay, when you are working in compressive, giving realistic values, okay? So here you give, let's say that, let me give a standard atmospheric pressure, okay? This is very important, okay? And now in boundary conditions, it's the same the setup, inlet, but when you go into inlet, outlet, and wall, see that now you're going to have a new tab, thermal. Now, besides giving velocity and turbulence intensity, in thermal, you can give temperature. So see here that I'm telling that at the inlet, the flow is centering with this temperature, Kelvin, 300 kelvins, which would like 30, will be like 30 Celsius, something like that. Okay, it's 275. So yeah, about, no, almost 30, yeah, it's 26 Celsius. Okay, and as you go now to outlet, see that in the outlet, also you have the thermal. This setup is exactly the same. And now thermal also, you set the backflow conditions. Remember we talked about what backflow conditions. And you go at the wall, also you will have now also that option enabled besides the standard ones, thermal. And you can set up temperature. And see that in this case at the wall, I'm heating that wall. So the flow is entering with 300 kelvins and the walls are heated at 350 kelvins. You have different ways, okay? You can set up heat flux, convection, whatever, it's okay. These are also different models. So I'm setting this one, temperature 250. It's a heated wall. And that's all, okay? These options, nothing change. Methods remains unchanged, pretty much the same, okay? And now see here that now that you have energy, also you have access to heat transfer rate. So I added that monitor to compute heat transfer rate. Okay, because if I go here, reports, let me go here, and that is a flux. Like the wall, see that I can know that I know my heat transfer rate, and also the method is conservative, so see that this quantity should be very low, close to zero. So it's not close to zero, but look at the order of magnitude. So the percent is very low, less than 1% of the overall. Okay, so you compute all your fluxes. Okay, so basically what I did here is just I put this monitor here. When you run, you can see all that monitor as well. And initialization. Okay, so you go to initialization, and let me show you standard. See that now you have a new variable. So see that you need to initialize also temperature. Okay, new variable, and when you run, just put it there. So let me run a few iterations so to show you. Let me switch off this. So see that here you have more equations, but basically because you have the energy. Okay, see the energy equation. Usually the energy also it should converge well. Okay, usually it's a low value for the tolerance. Okay, let me disable and let me run 50 iterations. Okay, to show you. So see continuity, momentum, energy, and turbulence model. So remember also the turbulence models, they have correction according now to the energy equation. Okay, so in this case, velocities are low, so we don't need to enable those equations. But sometimes if you have high-speed flow, shockwave, stuff like that, it is a good idea to add some corrections in the turbulence model. But here you see the quantities, okay, the convergence. So see that we restarted from a previous solution. Okay, we didn't need to restart from zero. Your mass flow, okay, so now it's a low quantity, y plus value, low values, and your heat transfer rate. Remember that also we saw in the theory that there is a correction to the y plus according to the Prandtl number, that now that Prandtl number exists here, okay? That is a quantity. We have the molecular one and also the turbulent Prandtl number. Okay, so let me finish running these 50 iterations just to show you also that we have that Prandtl number. So now we have more information. We can access more information when we are doing the post-processing. So besides the standard values, we're accessing also temperature, Prandtl number, stuff like that. Very important, just to remind you again, here now, as you are working in compressible flows, you cannot use anymore the dynamic similarity like in compressible, that the Reynolds number can control everything. Now here, you need to give the actual physical properties of the flow. Okay, so you need to give the actual physical properties of density for air or water, whatever, for the temperature, viscosity, and also you need to set up the reference pressure, because if you put that one that you are working in Bakun, we know that at the Bakun-Navier-Stokes equations, they break out, they are not valid anymore. Okay, so you need to think about that when setting compressible cases. Okay, in 3 more iterations, 2 will be done, and voila, we're done. So see here that you have the total heat transfer rate. And pretty much there are oscillations, but they are relatively low, you know, in comparison to the other magnitudes. So you have something about 3,500, and then the oscillations about 7. Okay, so it's very small, so you can take this for granted. That is a good converge solution. Okay, so just to show here, now you go here in graphics and see that now you will have this new tab, density. And as you plot here, you will be able to see the density variations. Okay, so see that according to temperature, we know that density will change. We have the equation of a state in this case, or you can put any equations according to you. Okay, then you have also temperature, a static temperature, so temperature variation. So at the inlet is cold, then see here that it get heated. Okay, the wall is heated. Probably if you rerun this case with a longer pipe, you're going to get a different behavior, no? And well, the rest for also problem velocity. Now also we might get access to Mach number. You have it there. Look at that. You have Mach number. It's a really low Mach number. You have access to that. You have access to speed of sound. So as you go here in properties, is what we call, see here that you have sound speed. Okay, you have sound speed there, and then also you have the constant, gas constant, CP, the molecular Prandtl number. Okay, and then as you go into the turbulent tab, you will see that here we have the turbulent Prandtl number. I don't see it somewhere. You should have that, but you have access to all those quantities. Okay, so this is how you do compressible cases. Okay, so in this case, the compressibility is due to a heated wall, but also remember that compressibility can be due to high speed flow. Okay, but the approach is pretty much the same. The turbulence treatment is pretty much the same. There are some different ways of doing averaging later when we deal with advanced topic. We're going to see that, which is called FAF averaging, which is kind of a mass weighted average, but the idea is pretty much the same as the Reynolds averaging. So this is all for this case. Okay, I hope you got the gist how to do the compressible case. So now we move to the final video where I'm going to show you how to do the post-processing, the Y plus in directing Fluent. By the way, remember here you have the lines, and if you want to save that information here, so you can go plot along the lines. See here that you have the same profiles. You can have also the temperature profile. See the wall is heated 350 and like this. So remember when we were looking at the theories, you have a laminar flow. You are not going to have this heat transfer rate like this. You have something different. Okay, so the heat transfer from the wall to the core of the flow is very different. Okay, so this is it. This is how you set up the case. As you see, it's pretty much the same. The only thing that you need to enable the new models here and here. Okay, thank you for your attention. See you in the next video. Bye.